Okay, so welcome everybody. This is going to be the last lecture of this logic course. And can everybody hear me? Would you say yes if you can hear me? Okay, great. Thank you very much. So we will finish the last part of the lecture 14, which is about Pressburger arithmetic. So and this whole thing is about more computational side of logic, which is decidability. In other words, whether there is an algorithm which when some formula is or sentence is given, that algorithm has to decide whether the sentence follows from what we call theory or not. So here's a quick reminder about the notion of theory. The notion of the theory is with respect to a specific signature. So when we talk about theory, we will always fix some specific signature. And then once the signature is fixed, theory is nothing but a set of sentences. Sentences are just closed formulas in first-order logic. And then, but the theory has to satisfy one condition, which is it should be closed on the semantic entailment. So if something follows from the theory that some sentence follows from a theory, that sentence has to belong to the theory. So it's closed on the semantic entailment. And then we talk about there are two ways of generating theories. One is fixing a structure A and just collect all the sentences that are true under that structure. So that's the first recipe. The second recipe is more syntactic. The first recipe is more semantic. The second recipe is more syntactic. And the syntactic recipe said, just collect a set of actions, which is going to be a set of sentences. And then from that set of sentences, we just collect all the sentence that semantically follows from these actions. So that's the second recipe. It's more like a syntactic approach to generate a theory. And then we said both recipes give rise to theories. And then what we are interested in is the specific property of a theory called decidability. And that property say, it is really about, it's an algorithmic, more computer science style question. It say that, it asks whether there is an algorithm that takes any sentence F, and then this algorithm should return and should answer the question that whether that given sentence F belongs to the theory or not. I mean, it's expressed in terms of a set membership, but really what it says is that given a sentence F, that algorithm has to say the sentence F follows from the some set of actions used to formalize this, generate this theory, or this sentence F follows is one of the truth of a structure which is used to generate this theory. Okay, so this is a kind of typical question that we are interested in, and then in fact there are many algorithms, actually implementations that implement this type of decision procedures for certain theories. And then we looked at one particular way of proving decidability, which is based on quantifier elimination. And quantifier elimination doesn't, it can be used to analyze a theory, not just for the decidability, for many other properties, okay? It's just very interesting or very useful properties of a theory. But in the context that we care about, it turns out quantifier elimination plays a very crucial role for showing a theory is decidable or not. Quantifier elimination, we say a theory admits a quantifier elimination if whenever we are given, maybe just using pen a little bit. So, so whenever we are given existentially quantified formula where f is quantifier free, so f may contain some free variable other than x, and if it is always possible to come up with a formula g which is quantifier free, such that they are equivalent under T, which means any structure satisfying all the sentences in T shouldn't be able to distinguish these two formulas. Okay, if the left-hand side of this, if and only if it's true, the right-hand side should also true. Left-hand side is false, the right-hand side should be false. Okay, so if we can come up with a G that is equivalent to this existentially quantified formula, then we said this is this theory ultimate quantifier elimination. Note that this part is really, really important. Okay, so we are not talking about quantify elimination for every structure. So we are not looking for this equivalence between exist x dot f and g on the every structure. We are looking for, when we are interested in structures that satisfies every sentences in the theory T. Okay, so the theory, we say theory T, ultimate quantifier elimination, whenever existentially quantified formula can be replaced by quantifier free formula. And we said there is a quantifier elimination procedure if this G can be computed from this existentially quantified formula. And then one reason we care about this quantifier elimination is because it allows us to have a proof of decidability, or it allows us to have an algorithm because of the theorem that we talked about last time. So that theorem said the theory T is decidable if it satisfies two conditions. The first, it has a quantifier elimination procedure. So it has one subroutine which take exist x dot f and return g in this sense. And then second, we can decide the membership of a sentence to this theory T if we just, if we can only focus on quantifier-free sentences. So for quantifier-free part, this deciding whether some sentence follows from theory T or not becomes quite easy. So that's what the second property is telling us. We can eliminate quantifier, and second, once quantifier is eliminated, we can decide whether a sentence follows from a theory or not. So if both of them are true, we can design an algorithm, and we talked about this algorithm last time. So then now the question, often this number 2 is quite easy. So for most of the case, this part is really easy, although we have to do some check, but the first part is really hard. And then that's the part where, in a sense, some new idea or some new insight is required. So last time we proved this quantifier elimination, this decidability by a quantifier elimination for the two theories. Okay, sorry. For the two theories we talked about, which is the theory of unbounded dense linear order, and then another, which is a theory generated syntactically. So it's based on a set of axioms. And another theory, we didn't really see the proof, but it can be proved in a very similar way. It's a theory called the theory of linear arithmetic over rationals, which is the theory generated semantically from a structure where underlying set is a set of rational numbers, and the operation we have is essentially operation from linear algebra. We have additions and constant multiplication and so on. And then the proof, in both cases, we prove they are decidable by this recipe. We first prove quantify elimination. And then second, we argue that in both cases, for quantifier-free formula, we can decide whether the formula follows from the theory or not very easily, essentially by evaluations. So that's what we did. And then today, we're gonna focus on something more complex, something more famous, which is so-called Pressburger arithmetic. Okay, so this is, you can think of it as essentially a number theory. So it's a theory generated semantically from a structure where the underlying set of the structure is a set of natural numbers starting from 0. So we have a constant 0, and we have a constant 1, and addition operator. And also we can compare two things using less than. So one important bit about this theory is that we don't include the multiplication operator. So actually what I heard is, mean, this Pressburger formalized this theory or axiomatized this theory completely. Although we are thinking about semantically generated theory, the same theory can be generated based on the syntax, based on a set of actions. And so the key difference between this theory and the one that we saw before, which is called piano arithmetic. So at that time, when we talk about piano arithmetic, we studied it based on the actions. But whether it's specified by actions or by the structure, it's a secondary. The most important part is that in one case, I mean, this piano arithmetic include multiplication. In the Pressburger arithmetic, it doesn't include multiplication. But including or not including multiplications, when we study set of natural or number theory from the logical perspective, make a huge difference. So if you start to include multiplication, this becomes undecidable. And then also, I mean, it's undecidable, and there are all sorts of problems like Gödel's incompleteness theorem applies here and so on. On the other hand, if we exclude multiplication, things become substantially easy. So it's gonna be, I will show you before, as I will show you before, this turned out to be decidable. And then, in fact, there are implementations which check decidability of a formula written in the Pressburger arithmetic. So in the very high-level message is that for number theory, once you start to include multiplication, things become substantially more complex. Right. So now let me just mention a few words about this, the person who is highly involved in the development of this Pressburger arithmetic, which is Pressburger. And Pressburger was a student of Tarski. I don't know whether I mentioned to you, maybe I mentioned to you a few times before. Tarski is regarded as, Alfred Tarski is regarded as a founding father of model theory and big part of modern mathematical logic. And then he used to be, I mean, when he was born, I think he was in Europe, maybe either Poland or Hungary. And then later he immigrated to the United States. But Pressburger was a student of Tarski when Tarski was in Europe. And then what we're gonna study was what Pressburger did during his master thesis. So this book, the result that we're gonna cover was actually part of Pressburger's master thesis. And then, I mean, he died very young. Pressburger died very young because I think he didn't really manage to escape from the invasion from Nazi Germany. So he was captured, and I heard he died in Auschwitz, so in the gas chamber. And then I heard like Tarski was devastated when he heard about the news. Okay, so let's move on to the real part. Okay, so Pressburger arithmetic, so it's over the signature, which doesn't include multiplication. So the signature for the Pressburger arithmetic include constant 0, constant 1, plus operation, and then equality. And they are intended to express number theory. Okay, so it's different from what we saw before, which is the linear arithmetic over rationals. There we are thinking about the rational numbers, but here we are only focusing on the natural numbers, which turn out to be more difficult. Although this signature is very limited, so we don't have a multiplication, so we can express something quite interesting. So the first thing we can express is that we can say every natural number is either even or odd using this formula, which say for every x there exists y, such that x can be y plus y, which means that x is an even number, or x can be expressed as x plus y plus 1, which means that x is an odd number. So we can say, using in the Pressburger arithmetic, we can say every natural number is either even or odd. And because it's Pressburger arithmetic is decidable, Actually, we can write a formula like this and then call a decision procedure, and decision procedure will say whether this is true or not. I mean, the computational complexity of decision procedure is horrible, so it may take for quite a long time, but in theory, it can return an answer, provide an answer for questions like this. So so here's one exercise I want you to do. So this is, I think Ben called it chicken McNugget problem, but I also heard this is sometimes called Frobenius problem. So this problem say the following. It said, so given A1 and AN, they are all natural numbers. They are constants. And we are interested in whether there is some number C, okay, some natural number C, such that all numbers greater than C can be expressed as a non-negative linear combination of A1 up to AN. In other words, if some number N is greater than C, and we are interested in whether that N can be expressed as linear combination of A1 times, so here's a non-negative number should come in, N1, A2 times N2, and so on. AN times, so N is a very bad, let me just write it, M. This is M1, M2, so this is Mn. So whether given for any M greater than C, whether it is possible to come up with M1 up to Mn such that they all have to be non-negative. If we multiply M1 with A1, M2 with A2, and so on, and then add all these numbers together, we want it to be same as M. So the question is, for every M, can we find M1 and Mn such that this equality is true? So that's this chicken McNugget problem. And then, so here's an exercise I want you to do, which is try to express this chicken McNugget problem for a given A1 and AN using Pressburg arithmetic. So A1 and AM are constant, so it can be like number 3, maybe 5, up to maybe 20. So these are specific numbers that we are given, and then the question asks you to generate a Pressburg arithmetic formula that express this this question. So I'll give you 2 minutes to do this. Okay, so the answer is actually, the next slide is the answer. And so we can express this proper problem like this. We said that exists X, which is the lower bound corresponding to C here, such that for every Y, And we write formula like this. So if y is greater than x, then there always exists z1 up to zn, which are the natural numbers. So they should be non-negative, such a way that y is equal to a1 times z1 and so on. And then here you might wonder, I said that in Pressburg arithmetic, we can't really express multiplication. So how come we can have the multiplication? You may have a question like this, but important bit is that this a1 is a constant. It's not a variable, like number 3. And an is another constant, like number 20. So if we have a multiplication and one of them is a constant, natural number, then we can actually express it as in terms of additions. So if it's a constant 3 times z1, we can write it like a z1, z1, and z1. And if it's a 20, this is going to be much more clumsy, but we can write it like zn 20 times. So in a sense, in terms of, this will explode the size of the formula, but in terms of expressivity, in the Pressburg arithmetic, we cannot have general multiplication of two terms, but we can have multiplication between constants and term in this Pressburg arithmetic. That is okay, because we can encode it by just, if it's a term, addition of terms, this constant number of times. Okay, so Pressburg arithmetic is limited, but it's not that limited. That's because we can, encode some of the multiplications inside the Pressburg arithmetic. Now, interesting bit is that, just as I said, because it has a decision procedure, what it means is, we can design an algorithm by calling the solver for the Pressburg arithmetic. So how should we, that answers solve this chicken McNugget problem. How we do it? Given numbers from a1 up to an, we generate this Pressburg arithmetic formula. So that's a step 1. And then step 2 is we call decision procedure for Pressburg arithmetic. And then the decision procedure, if it say yes, then that means the chicken McNugget problem has a solutions. If we say no, then that chicken McNugget problem has no solution for the given instance of a1 up to an. Okay, so let's talk about expressivity, but because of the nice property of Pressburg arithmetic, it can be used to come up with an algorithm. Of course, there may be an algorithm that is much more efficient, but at least this gives a baseline. Okay, so now the question becomes, we would like to show that Pressburg arithmetic is decidable, and using the kind of tools that we learned so far, which is Quantifier Elimination. But it turns out, just applying the Quantifier Eliminations to show this Pressburg arithmetic, decidability of Pressburg arithmetic, turned out to be quite hard, or actually impossible. That is because it doesn't permit the Quantifier elimination. Okay, so for instance, now think about a formula which say there exists y such that x is equal to y plus y. What does it mean? That means that x is an even number. Okay, so that's what this formula is telling us. But without using any quantifications, using this, although it requires some proof, without using quantifications in this over this signature, we can't really express the write down a first order logic formula, quantifier free first order logic formula over the signature, which say that x is an even number. Okay, so I didn't give a proof, but if you try it, you might feel that it's very difficult, which give a good indication, although it's not always the case. It's a good indication that it's impossible to write a quantify free formula for even numbers. And it turns out that's actually true. So what should we do? So this means that the recipe that we talk about doesn't really apply. So the one things that we will do here is to actually, we will extend the signature with some extra predicates. Okay, so we will add a bunch of more, actually countably many more predicates to the signature. And we will interpret these countably many predicates under this usual structure of set of natural numbers. So the operation that we are adding is of this form. This means divisibility. Okay, so the C is a natural number. Where C is greater than 0. And this talk about divisibility. So it's like say this 3t means that term t over the signature is divisible by 3. And this means term t is divisible by 2. Okay, so by using this divisibility relation, divisibility predicate, we can say something is an even number. And it's quite easy. We can just write it like this. That means x is divisible by 2. So that's equivalent to say x is an even number. Okay? So we add all these predicates. So note that this C part is a constant. It's not a term, it's a constant. And then we are adding infinitely many or countably many predicates into the signature. And then think about its structure using the set of natural numbers. Okay. So this divisibility, you have the usual meaning of divisibility. So it turns out if you do this extension, this extended the theory over this extended structure has a quantifier elimination procedure. Okay. So that's what we're gonna that's what we're gonna. So this theorem is proving this theorem will form the main part of today's lecture, the remainder of the lecture. But before moving further, I want you to assume that suppose we have this quantifier elimination procedure for this extended signature, and then using this, show that the Pressburger arithmetic is decidable. So Pressburger arithmetic, sometimes when people talk about Pressburger arithmetic, they are referring to this extended signature, sometimes not. But at this particular exercise, let's say Pressburger arithmetic without this extension, we want to show that it is decidable. But I'm saying if we extend the signature and then interpret it using the usual set of natural numbers, this has a quantifier elimination procedure. So using this theorem to prove the theorem that's shown in the beginning of the slide. So I will give you 3 minutes to think about this. Okay, so let me show you this, how to do this. Okay, so let's call the, yeah, this, the structure for this, signature for this structure to be sigma. And because the signature for this structure to sigma prime. So sigma prime is a sigma together with in some bunch of extra stuff. Okay, so then under this, let's try to prove the first theorem. So the theorem says it's decidable. This means we have to come up with an algorithm. So what's the type of what this algorithm does? Let's say it's a decide Pressburger. So it takes a sentence F and you have to return either true or false. So okay, we just use Python-like notations. So you have to return true or false. So that how should we do it? So you first call Quantifier Elimination for using, so this F is a formula over signature sigma. So then we call Quantifier Elimination for signature sigma prime because that exists because of the second theorem, and call F, then that will return F prime, okay, which doesn't have any quantifier. But one thing you need to notice is that although F is a formula over sigma, because we call the quantifier elimination over sigma prime, F prime may be a quantifier-free sentence over sigma prime. So it may use this divisibility predicates, which we added when we define sigma prime. So this F prime is the quantifier-free sentence over sigma prime. So to answer this question, we have to decide whether F prime is an instance of this extended theory or not. Okay, so then it turns out this is quite easy. It's an extended quantifier-free Pressburger F prime. And then we can just take a result. But then this extended, this part was quite easy. That's because if F prime is a first order logic formula, quantifier free, which only uses 0, 1, plus, less than, and so on. And this is really, you can view this as an arithmetic expressions in normal programming language. It's a term constructed with 0, 1, plus, well, actually it's a Boolean expressions. It uses less than, and then it uses like a divisibility and something like this. This is nothing but in normal programming language. It's a something 0 mod 3. So yes, if we divide it, it's do the natural divisions and see that whether remainder is equal to 0 or not. And then because it's a formula, we may have a conjunction, disjunction, and negation. But this is the kind of things that you typically see in typical programming language. And this is because it's a quantifier free, it doesn't have it. And it's also F prime is a quantifier free, and F prime is also a sentence. It doesn't have any brief variable at all. So we can just do the evaluation and see whether it's true or not. Based on the evaluation. And then this if it returns true, that means this F prime is equivalent to true under this structure, under this theory. And if it's false, that's equivalent to false. Okay, and then because true is always in the theory, true is true is implied by any formula, so true is always in the theory. In the first case, we just return and said F prime belong to the theory. Second case, I mean, false is never be in the theory generated from a structure. In the second case, we can just say f prime is not in the theory. So it is a yes and no. Okay. So that is some justification, but from the algorithmic perspective, this decide extended quantifier-free Pressburger sentence is just doing evaluation in the standard sense in programming languages. And then if the outcome of the evaluation is true, then we just said true, otherwise you return false. So that's how we can design an algorithm. But so that's why this second theorem implies the first theorem. Now then the question becomes, how can you prove the second theorem? It is actually quite involved. But the proving, so we're gonna focus on this quantifier, so the proving that this theorem, but the proof about quantifier eliminations has the same format as before. What should we do? So we are given, assuming that we are given formula exists x dot f. So this is the input. So then input is exists x f. And then we want to come up with g such that they are equivalent under this theory. So this g is what we want to get. And then this quantifier elimination procedure works in 2 steps, just like before. The first step is to massage this exists x dot f just based on the usual rules in the first order logic, very generic rules of first order logic, such a way that existential quantification is over very simple formula f. So in a sense, the first step, we want to make this f as simple as possible. So that's what this first step is trying to do. Second step is once this f becomes as simple as possible, so then we can start to look at what type of theory we are having, because these are the kind of facts we can assume to show the equivalence. So what kind of theory we are having, and then we use this information from the theory to replace this, to get rid of this existential quantification. So now how the first steps work. First step is like the one that we see before. So just give you a reminder about this. Okay. So the step 1, it consists of multiple phases. The first phase is removing negation. Okay. So we move negation using De Morgan's law from a given formula exists x dot f. So then we push negation all the way to the base case, and then for the base case, we can get rid of negation by using some fact about the less than relations. Okay. For divisibility, we can also get rid of negation. We have to do some work, but the idea is really simple. Moving negation from all the way to the base, this atomic predicates, and then for atomic predicates, the prime can be removed. Also, CT, it can also be removed by doing essentially case analysis. So that's a first step. So we move negations. So say we start with exists xf, and then we remove negation from f. So then let's call the resulting formula f prime, and we convert f prime to DNF form. So we apply DNS transformation f prime. This will give us f double prime, which have in the format like f double prime 1, disjunction, f double prime 2, disjunction, and so on. And then the third step is to use the following rules. The following equivalence, which is that if we have exists x G or H, this is equivalent always is XG or exists XH. Okay, so this is always true. So existential quantification can be distributed over disjunctions without changing the meaning of formula at all. So if we do apply this, then we end up with this X F1 double prime. This is X F2 double prime and so on. And then the last step of the transformation was we used the, again, transform based on the another rules, which said if we have an existential quantification and conjunction, and this is equivalent to exist XG, conjunction can be taken out when H doesn't contain X. Okay, so what does that mean? If we apply this transformation, we can move this F1 double prime because we are this F double prime was DNF. F1 double prime should be a conjunction of literals. Okay, so then we can group those literals which contain X, those which doesn't contain X, and then we can move kind of regrouping such a way that this existential quantification is over the literals that contain X. So really, at the end, the formula that we obtain is this form. So this disjunction corresponds to the disjunction that we obtained in the step 2 and 3. And then now this existential quantification is kind of moved to the scope of existential quantification is narrowed by moving this existential quantification because of what we do in step 4. Okay. So after this whole transformation, we get exist X, FL, and then FL prime, where FL prime is a quantify free because we are starting with the original quantify free formula. And then it doesn't contain any X containing X. And then FL is a conjunction of atomic predicates. Because the negation is all gone, we have just conjunction of atomic predicates. And then these conjunctions can be written as follows. Actually, it's not exactly equal, it's semantically equal. It can be written like this. So if we have some cases where, all of them contain X, some cases where X contains the right-hand side of this less than relation. So X is on the greater part of this less than relation with multiple copies of X. So this AI is always a constant, just some constant. And then this is a term. And then also another possibility is this AX appears the left-hand side of this less than. So again, this is a constant. And then this is a term. The last bit is we have a divisibility predicate used where, and then X appears in the predicate. So this X appears here with AK copies of X. Now the one thing that I want to gloss over, I didn't really want to go into the detail now because it may confuse you more, is that actually, expressing something like this actually needs some tricks or some convention, which is that although in our Pressburg arithmetic, we don't have any negation, we should include, in most general case, if you try to do the transformation, Qi y bar may contain and minus sign, but this minus sign should be understood as some form of macro. Okay, so more details you can find it in the lecture notes, but I'm not going to talk about it. That's because already things are quite complex, and then you will get completely confused. Okay, so say this is a part which I'm not, which most in general case this may happen. So this Qi Pj may contain minus sign. We should have followed some convention to interpret what that minus sign actually means, but I'm not going to deal with it. So what I'm going to assume now is that just Qiy, Pjy, they are terms over this specific signature that we are dealing with in the signature of the Pressburg arithmetic. Okay, so this FL has this form, and then the important bit is now is to get rid of this existential quantifications over FL. So we have to transform this exist XFL, which is this part, to a quantifier free formula. Okay, so that's the part that we want to focus on. So the step one, most of the time, as I said, is like what we did before, except there are some subtleties about the dealing with the negation. But ignoring these subtleties, the formulas of FL will have this form, conjunctions of something about the lower bound of X, something about the upper bound of X, something about the divisibility involving terms on X. Terms that involves X. Okay. So then we want to get rid of existential quantification over this very much simpler formula than arbitrary for Pressburg arithmetic formula. So the question is how to do this. Okay. So we will focus on this step 2. So here's again some reminder about what FL actually look like. Our goal is to eliminate quantifier exists X from FL. Now this quantifier elimination consists of 2 steps. The step number 1 is to, in a sense, replace exists XFL by another existentially quantified formula. But so we're gonna, okay, so maybe just write it here first. So we will change this exists XFL to something else. Exists X, I forgot, maybe HL. They are logically equivalent under the theory. Okay, so under theory, they are say that exactly the same thing, but this HL is a bit simpler in the sense that the coefficients that appears in front of X or coefficients in front of X are going to be 1, I think. So here's how we do this. So yeah, it was not actually HL, it's just H. Okay, so before actually seeing the statement, let's try to look at, so this is the H that I'm talking about. So before actually doing anything, let's try to look at, in which sense this H is a bit simpler. You can see that X appears here, in the 3 different places. Then actually there is one more term about X. But if you look at the coefficient in front of X, they are all 1. Okay, so coefficient of X here is 1, X is here 1, 1, and 1. On the other hand, in the original formula that we started with, coefficients may be AI, which means that actually if AI is equal to 2, there are 2 copies of X here. If HJ is 3, there are 3 copies of X here, and so on. So in this sense, by reducing, by doing some transformation, we make it a bit simpler. So this coefficient become all 1, except that we add some extra things which talk about divisibility. Now, the key part of this transformation is this quantity B. So this B is a list of, okay, maybe I'm using red is better. So this quantity B, so this B is a least common multiplier. In Korean, it's called 최대 공약수, 최소 공배수, 최소 공배수. So it's a least common multiplier. And then this B is a least common multiplier of all the coefficients of X appearing in FL. So, okay, we collect these XI, AI here, AJ from here, AK from here. We collect all of them. So they are all gonna be natural numbers, which are greater than or equal to 1. And then we compute their least common multiplier. That they always exist because it's a finitely many and you can always compute least common multiplier. And then because B is a least common multiplier of all these AIs, okay, if you divide B by AI from some AI from the first case, or divide B by AJ from the second case, B by AK, they are all gonna be natural numbers because B is a least common multiplier of AI, AJ, AK. So if you divide them, then you will also get a natural number. So the transformed H is obtained from the original FL by removing this coefficient of all the X and then multiplying B divided by AIs on the other side. Okay. So you can think that B, this AI, in a sense, moved to the other side, but after dividing B, it's in this form B divided by AI. And the same thing happens here, and the same thing happens in the last case. So in some AK go into the denominator of this fractional number, but we put B on the top. So you can see that this B divided by AK appears everywhere, except we add one more term which said B should divide X. Okay, so the first exercise I want you to think about, I will give you 2 minutes, is that this exists XFL and exists XH, they say exactly the same thing. They are equivalent on this theory of natural numbers. The standard natural number structure of piano arithmetic. So try to show why that is the case. So I will give you 3 minutes to think about this. Okay, so let me tell you why that is the case. So what we have to show is, we have to prove exist XFL and exist XH, they are equivalent. But the existential formula really means, what does exist XFL means? It means that the formula, this constraint that we wrote about X has a solution. So that's what exist XFL means. Exist XH means that the constraint that we wrote at the bottom has a solution. It's a constraint about X, this has a solution. So now, so to show these equivalents, what we have to prove is that if the constraint FL has a solution for fixed y, if constraint FL has a solution, precisely when this constraint H for the same fixed y has a solution. And so that's what we have to prove. So now we have, and then it turns out you can actually do it. The way you can do it is, if X is a solution for f of L, then if you multiply X by B, so B is some fixed constant. Because all these AIs are constants, B is some fixed number that we compute from this formula. So given X, if you multiply X by B, it turns out this becomes a solution for H. If this is a solution for FL. And by on the other side, if we have a solution Y for H, so then if we divide Y by B, then this turns out to be an integer, natural number. And it also a solution for FL. Okay. So this turns out this fact is true. And so first, let's see why this fact implies this equivalence. This equivalence said, because this XFL means there is a solution of FL, because XH means there is a solution for H. So if this transformation and the property that I told you is true, if FL has a solution, then if we just multiply by B, we end up with a solution for H. So if exists XFL is true, exists XH is gonna be true. On the other side, and also if exists XH is true, then we have a solution Y, and then this transformation say Y is actually divisible by B. If we divide it, then that's going to be a solution for FL. So in that case, FL will also have a solution. So this shows that these two things are equivalent. And why this transformation is okay, and actually this for these transformations, the fact that I told you here, you can actually check quite easily. So just by doing transformation. So let's say X is a solution for FL. So to see, change the color a little bit. So to see this implication, let's say X is a solution for FL. Okay. So then that means now we multiply X by B. Okay. So we want to claim that B of X is a solution for H here. Okay. So instead of, although we wrote X at the bottom, let's write it. Let's call it this is X0, which is a B of X0. Okay. So if we write it for, we just check whether that's actually the case. If we write B of X0 here, this is also going to be B of X0. And here is a B dot X0 and B dot X0. Then all of these constraints has to be satisfied. Now the last constraint is true because B multiplied with something is divisible by B. So this is okay. And the first one is now if you do some multiply the entire both, okay, for first one is also okay. That is because if you right. So if this constraint is true for X0, because X0 is a solution for FL. So we have a Qi Y bar less than AI x0. Now, if you multiply both sides by b0, b, that means we're gonna add the right-hand side at b times and so on. Maybe just so write down b of AI. And then, so if this is true, then the one above is going to be true. Now, if I divide AI from both sides, this will also be true, okay, for a specific number x, and then qi y bar. But now b is an integer. B divided by AI is also an integer because b is a least common multiplier. So that shows the constraint that we are talking about is true. So you can reason like this. So for this upper bound, we can do the same kind of reasoning to show that this upper bound for FL, this implies the one below. And the same thing for opposite direction is the same, assuming Y is a solution for constraint for H. And because of the last guy, I mean, this Y have to be divisible by B. Now, once you divide Y by B, you can, for each, using just each constraint of H, each conjunct of H, you can show the constraint of FL is all gonna be true. Okay, so that's how you can prove this exercise, solve exercise 1. The next exercise is actually a bit more challenging. So the next part is that, so we, using this step, we transform exist x FL to exist x H. So exist x H, x doesn't have, I mean, all the coefficients of x is now equal to 1. The last part is now really removing this existential quantification. So, okay, so okay, let's just mention both of them. So the idea of removing existential quantification is follows. This exists x dot f h. Maybe you write it on this side. So for exist x dot h, so let's think about the first case where we don't have any lower bound. So the case where L is equal to empty set. So then something funny happens, okay? So we view H as a constraint on X. So then what happens is that if there is some number C, so that if X is a solution for H, then X minus C is also a solution. Let's call it X0 for H. So here, C is computed by this one. It's also least common multiplier of B, which is we computed in the previous step, and or the B times CK divided by AK, or so what's this least common multiplier? I mean, this least common multiplier. So this is C, which is a least common multiplier, really coming from by looking at all these the constant that we used in the divisibility constraints in H. So we collect all of them. So which is B, and then the B divided by AK times CK. We collect all of them and we compute their least common multiplier, their 최소 공배수. Okay. And then this C is that number. But interesting bit is if L doesn't have any lower bounds, then this constraint, the solution for H has the following property. If X0 is a solution, then subtracting from X0, C from X0 also gives a solution. And actually vice versa. If X0 subtracted with C is a solution, then adding C is also going to be a solution. So what does this mean? This means that, okay, so that's a property, and sorry for being hand wave in many places, but I think it's more important to get a big picture than the actual, all the details. Right. So what this turned out to be true, right? And you can actually check that this is the case. So it's a bit like before. We think about solution transformation, which maps a solution to another solution. Okay. So this is true. Then if this is true, what can happen is that suppose x, this C is say 30, and x0 is like 134. Okay. So then if this relationship is true, then by changing this x0, keep subtracting 30, we can come up with a solution which is smaller than 30. Okay? Because if we subtract 30, then the result is gonna be 104. That is, if 134 is a solution, 104 is a solution. If you subtract 30 again, then 74 is a solution. So if you keep doing it, then 14 has to be a solution. So what does that mean? That means that if there is a solution for h, for any natural number, there has to be a solution which is between 0 and the number 30 in this case. Okay. So some number between 0 and 30 has to be a solution for this problem. So that's what this constraint is telling us. Take h and then plug in all the numbers between 0 and c, and then conjoin them using disjunction. Okay. If one of them is true, so what this m means that m can be number 0, number 1, number 2, and so on. And each of hm for x means that m is a solution for the constraint h. So if one of these disjunct is true, then exist xh is true, because exist xh just means there exists a solution. This one below, say m is a solution. So it's a much more stronger statement. But because of the property that I showed you here, if there is any solution, that solution can also lead to some solution within this range between 0 and 30. So that means that if exists xh is true, one of the disjuncts below has to be true. So this relationship also has to be true. So that's so just to sum up, what I did was I think about the solution transformations, which preserve if something is a solution, the transformed version is a solution. Let that transformation keep making the solution smaller and smaller, so that what we can claim using this fact, we can show this existence of a solution becomes equivalent to existence of a small solution. Now the one below is about the lower, we should consider the lower bound. So really, okay. So the one below is about the lower bound. So the one below is thinking about all the cases where so what we really want to say in the lower bound case is the following, which is that if you consider the maximum of so this, I mean, this is not a Pressburger arithmetic formula. But intuitively, this conjunction is equivalent to say x is greater than the maximum of all the lower bounds. Okay, so then we apply the similar strategy as the first case, except that now the lower bound, instead of starting from 0, go all the way to 30, it starts from this max b AI, QI, Y bar plus 1, because it has to be a greater than this lower bound up to the same term plus 30. So the range is exactly the same, but we want to start, instead of from 0, we want to start it's a maximum. So the disjunction that you see is a way to encode this idea using the Pressburger arithmetic. So I hope that you get some key idea. Key idea is that we view FL as a constraint over X, and then we keep transforming this FL into some different constraint, which is a bit simpler, but say but it's in a sense equisatisfiable in some sense. One constraint have a solution, then we can generate a solution for the other, and vice versa. And now for the constraint H, we are looking at what kind of solutions it can have. And then the last step is about if H has a solution, then the solution should be within certain finite range. So using that fact, we can get rid of this existential quantification. Okay. Right. So then the actual computational complexity for the Pressburger arithmetic based on the decision procedure for Pressburger arithmetic is horrible. It's actually not too bad for this type of logic. It's a exponential of exponential of exponential, but sometimes things become very bad. It has a tower of exponential, so this is a bit better. But still, it's a very highly complex. I mean, it's a big number, but still, in practice, some of these decision procedures work reasonably well. Okay, so for Pressburger arithmetics, I mean, there's a very nice article by Christopher Haas. So he's one of the person who teach the same course at Oxford. I think now he's in UCL. And then his article contains description about all the things that I've talked about, which also appears in the lecture notes, but also a lot more about like many other applications or much deeper connections between Pressburger arithmetic and other aspects of theoretical computer science and mathematics. So in the remaining 2 minutes, let me just mention a few words and then finish this entire course. So the logic, I came to, maybe not much now, but when I first do my PhD, I really liked the logic. But the type of logic that I liked was a bit different from what I presented to you now, which the logic I liked a lot was so-called proof theory, which is highly connected to the design of type systems in programming languages and interactive theorem proving and so on. So that's some aspect of the logic we didn't really talk about. Instead, we focus more on the side of logic, which is more computationally oriented. Okay, and the one thing I want to mention is that the logic is a very broad. We just focus on the one aspect of the logic, and then it has some other things like proof theory that I just told you, as well as something called the model theory, which turn out to be good tools even for mathematicians, so that it can lead to solutions to some open problems in mathematics. So, and then all these things about the logic, the one message I want to convey throughout the lecture is that although they are sometimes very theoretical and also sometimes very mathematical, they have an implication, so they have a connection with computer science. Proof theory has a big connection with computer science, design of programming languages, interactive theorem proving. The kind of logic, what algorithmic logic has obviously have a big connection with decision procedures in logic and so on. Model theory also has good implications in the semantics of programming languages, and also it plays some roles in understanding some of the decisions, some of the algorithms. So I hope that I just kind of make you more interested in logic a little bit, so that I hope you continue to explore more aspects of the logic in the future. Also, thank you very much for all of you to attending. This is not very easy course with many very hard exercise, but I'm thankful for all of you who spend quite a bit of energy to follow the course. Okay, so thank you very much. For about the exams, the exact information about the exams will be available in KLMS. Yeah, as usual, I wait about like 5 more minutes to make sure if you have any questions, you can ask me.